Okay, let me introduce briefly the session. It's good that we have a full house. It's bad because they ran out of lunch boxes. They're gonna bring a few more. I don't know the logistics, but out there or so at some point, if you didn't have a chance to get a lunch box, they may fix it for you. I don't know. There'll be a few more. Okay. Excellent, thank you. Okay, so moving on into this session, as you know, the global host usually arranges a session of something that could be of interest to the ITF crowd. So last time we did this, it was also John talking about security, and this was a few years back. So we thought that it could be interesting to present how some of the Ietf technologies that they are developed here, they are used in actual networks to secure networks, in this case 5G networks and 6G networks, which is what Ericsson develops and deploys. So without further ado, I would like to give the floor to John, and I hope you like understanding how, again, the ITF security technologies fit into the system architecture of 3GPP concretely 5G and 6G networks. John, please.
Thank you, Gonzalo. So yeah, if you don't know me, I've been working with Ietf and 3GPP standardization for the last 15 years. Last 5 years also very active in NIST standardization, worked also with other things. I'm also doing strategy and requirements and operational work with our products at Ericsson. And this will be about migrating telecom to quantum-resistant cryptography. So 4G, 5G, and 6G, they are really, truly global standards. Today, you take it for granted that you can take your phone and you can go all over the world and you have connection. That didn't at all used to be the case. 2G and 3G were fragmented. 4G was the first truly global standard, 5G is same, and very hopefully and likely 6G will also be a truly global standard. So what are some of the characteristics of the telecom industry? One difference between many other industries is that it's highly regulated. One reason for this is that the telecom industry uses licensed spectrum, which basically the government have to give you the right to use. This complicates things, but also gives you, there is nobody disturbing you, so you have this spectrum for free. Other reasons is that telecom companies typically used to be state-owned monopolies. That is often not the case anymore, even if there are some company operators are state-owned, but many are private. But this lives on. Telecom has a very high reliance on standardization, and typically standardization comes before development and deployment. Not really done in parallel, at least not in the past. The telecom sector is also moving to more agile thinking. I would say 3GPP is maybe the main standardization body. Then you have ORAN for Open RAN. You have GSMA for services and interop between operators. Telecom is definitely considered critical infrastructure all over the world. Then critical infrastructure is maybe not well defined. In the last years, decades, and in the future, telecom mobile networks is increasingly used for public safety and industry. In addition to public networks, there are now also private networks that can be used for industry, and these can be completely private or part operated with some existing operators. And in large part of the world, we are seeing these old dedicated networks being replaced with 4G and 5G for police, fire, and ambulances. There also increased use of mobile network for defense purposes globally. This comes with even higher security and privacy requirements. Telecom sector has quite rapid technological evolution. Sometimes it's a bit stuck in generations, so you need to wait 10 years until you do something new. But there's also a lot of development ongoing in releases, both in standardization and maybe even more in deployments and vendor products. Quite high competition and consolidation, and there's a lot of different players. You as consumers might know the operators and the smartphone vendors, but what you don't see so much is the infrastructure vendors. This is infrastructure built by Ericsson, where I represent, and then you have a lot of chipset vendors that come into smartphones, as well as infrastructure things in the core. So a little bit history of quantum and security that some of you might be aware of. This is very, very, very hyped now, maybe a little bit too hyped. But a lot of the algorithms that we are now starting to deploy are actually quite old. Code-based and hash-based cryptography are from the 70s. They are as old as Diffie-Hellman and RSA. It was just that they were not as effective, and nobody thought quantum resistance was important in the 70s, 80s. There were no quantum computers. The realization and urge to move to post-quantum, I would say, was really starting in 2015, when NSA announced that it was planning to move US national security systems to quantum resistant. Has been a lot of talk before that, but I would say this was the thing that really got people to consider this critical and a real thing that will happen. 2022, US government released CSNA and NSM-10 with timelines and algorithms. Timelines for general and algorithms for natural public safety. 2024, what is important for basically all use cases is NIST published the final standards of cryptographic algorithms, and MLChem, MLDSA, and SLH-DSA. And I would say these will be the main ones used. There are other algorithms, but they will probably be much smaller use case, at least right now. 2025, we got timelines from European Union and the UK. They are different a little bit, but in general, they all say you should migrate high priority systems around 2030 and all systems by 2035. And if you have done any migration of cryptographic algorithms, you know this is quite short time to do that. It takes years and sometimes a decade. Can talk for other, but for Ericsson, MLChem, MLDSA, and SLH-DSA are now mandatory upgrades for all products, written in requirements applying to all products, and QKD is forbidden to use. So where are we when it comes to the quantum threat? This is a very nice picture by Sam Jack that he updates every year. The little gray box is where quantum computers are now, and the red lines are where you need to be to break RSA. This is a so-called cryptographically relevant quantum computer. And other systems like elliptic curves is similar. And this is a logarithmic scale, so there's quite a lot of distance from where we are now to where you need to be, and a lot of uncertainty when that would happen. I would say it's quite not very likely it happens in the next 10 years, but it's not unlikely that it happens in 2030. A lot of uncertainties. If you take like Moore's law, it would take 25 years. Currently, quantum computers are growing much slower than doubling every second year. But if they start growing much faster, it could go faster. Very uncertain. Another question mark is how long will people invest in quantum computer if there are no use cases? If everybody moves to PQC, breaking RSA will not be a use case anymore. And quantum chemistry is typically touted as the best close application. I just heard some presentation from a quantum researcher say she didn't believe in that at all. So it's a lot of uncertainties. But it's definitely moving forward. There was a breakthrough last year where several companies, Google and somebody else, built the first logical qubits, doing error correction for the first time on physical qubits. So it's moving forward, but slowly, very uncertain when it comes. But for telecom, this is not really a topic anymore. It doesn't matter when they come. Government regulations and requirements are very clear. You need to migrate soon. So when and if quantum computers actually come is not important. If you don't need to follow government requirements, then you might need to look at this. If you need to follow government requirements, then this doesn't matter. You need to migrate, and you need to do it soon. So what are the migration timelines that have been published? As I said, we will go to the next, but in general, they say prioritized systems by 2030, a little bit different views what a prioritized system is, and basically all systems by 2035. And if you update software, then 2030 is, it's not so many years left. You need to plan this now. And if you're updating hardware, 2035 is not so far ahead. You need to plan now. In general, all governments require standards, standardized PQC algorithms, and they don't endorse QKD. And in general, all the government's requirements are for deployments. This I've seen many people in STOs and companies mistaking. You don't need to have standards ready by 2030. You don't need to have products ready by 2030. All deployments should have 100% PQC 2030 and 2035. So standards and products need to be done much, much earlier. 2035, you should take off all the devices that are not PQC firmware update. That's what requirements are saying. If that is realistic or not can be discussed, but that is what the government requirements are saying. This is NSA, US government, took that because it's very detailed and good. I think NSA is not using that anymore, but I agree with NSA that software and firmware signing is very prioritized. If you buy a product in a couple of years, you don't want to throw it out in 2035 if it's otherwise working. And firmware update, you can typically not update the roots of trust after manufacturing. Here are the migration timelines for a lot of other countries. Up here we have the UK. This is the European Union. Here is Canada. Here is NIST. And here are the French requirements. And as you can see, they're a little bit different in what they think is high prioritized and the deadlines. With the current French actually saying PQC is recommended everywhere, 2030, also low prioritized and also firmware update, and the current Canadian saying very loosely in the 2030s. But I would expect these guideline requirements will be updated a little bit more. US NIST is saying disallowed 2035 without much more details. So where are RSA and ECC primarily used? And this is very similar in telecom network as in any other ICT systems. And So same thinking and processes apply. They are typically used for signatures for firmware and software update. And the reason why you need to prioritize thinking about this is because you can typically not update these after manufacturing. Then there is short-term signature for authentication. These are also not urgent, but updating and migrating PQC takes a lot of time, typically a decade. So you also need to think about this. Binding signature for non-repudiation, like if you have digital contracts, you need to update these. This is something people typically don't talk about so much. It's not really related to ICT, but most companies are doing digital contracts. And then you have public key encryption and key exchange. This get a lot of attention because of harvest now, decrypt later. But basically with these timelines, there is not so much prioritization to do. You need to start migrating now and have roadmaps for how and when to migrate. If you do a product update, you should probably migrate to PQC. So in communication, public key, typically you can hear that 3GPP uses symmetric key cryptography. That was maybe true in GSM. Nowadays, 3GPP and 5G networks use public key cryptography basically everywhere. It's used in all layers of the network stack, from application to the link network transport. And just like in the Ietf and the web, there's been a trend to move things upwards in the application, in the stack, from link to network, from network to transport, from transport to application, to get more flexibility and also to get easier get end-to-end encryption, not just some segue to segue. So can quantum technologies be used for security? And it's a mixed answer. There's a lot of discussion on QKD. If you were at the side meeting last in Bangkok, Germany said that QKD is absolutely not mature for deployment. Maybe it can, and I say maybe it can be used for defense in depth in 20 years. And the comment to that was from Swedish government, which didn't agree and say it will never be useful. And somewhere there, even mentioning QKD right now is a distraction. And if you believe migration, making things quantum safe today is important, then any distraction is dangerous. Same thing with quantum random number generation. They are not mature, and both of these things doesn't really solve any existing problems. They are just hype. In many cases, they are not mature. They are not solving, they are exacerbating existing issues like availability and trustworthiness. Typically, both QKD and QRNG are very sensitive. Somebody said they have seen, they don't work at day, they don't work at night, they don't work when it's dry, they don't work when it's moisture. Yeah, they don't work when it's cold, they don't work when it's warm. So I also seen a lot of demonstration that doesn't work. And availability is one of the three important things with security. You want confidentiality, integrity, and availability. What quantum can be used for, which is maybe talked about way too little, are quantum sensors. They are extremely promising for military use. And they're already getting deployed. You can use quantum inertial system for navigation. You can detect submarines with magnetometers, and you can detect tunnel and bunkers with quantum sensors. You can also use like magnetometers to do navigation and gravitational sensors to detect submarines. So a lot of use cases. Not so much use in industry. They're still very expensive and very big. You can like put them on a big boat if you have. So not really useful for telecom right now, but maybe in 20 years you can use them for antennas, for example. So how does the 3GPP network look like? This is an overview of the 3GPP 5G connectivity layer. And all the red ovals are places that use public key cryptography. And these are the places that you need to upgrade the algorithms to be quantum secure. The orange boxes are proprietary 3GPP protocols, and all the green boxes are Ietf protocols. And as you can see, there's a huge overlap between green and red ovals. Not only is Ietf protocols extremely important for 3GPP, Ietf protocols are used for like 99% of the public key use in the 5G connectivity layer. So Ietf is have an enormously important part in making 5G quantum safe. Unfortunately, Ietf is sometimes skipped. I've seen governments, telecom people, and so on talking about in their head, NIST is standardizing the algorithms, and then 3GPP will do the rest. But I would say Ietf is maybe more important than 3GPP in these aspects. For DTLS and IPsec, whatever is registered for IPsec and TLS can be used immediately in 3GPP deployments. You don't need to wait for 3GPP. You probably know many of you already know what is happening to PQC in Ietf protocols, so I will not talk too much about that. Maybe more interesting parts are then the IMSI encryption, here named Suki. So you might have heard about problems with IMSI catchers. In 2G, 3G, IMSIs, the identities of your SIM card are sent in clear, they are not encrypted. So anybody, if you have some sophisticated equipment, you can eavesdrop on this communication and see the IMSIs and then tie them to a specific user. In 5G, it's standardized how to encrypt the IMSIs, and this is done with ECIES. If you have followed TLS client hello encryption, they're using very similar. You have a pre-established public key, and then you encrypt the identity or the client hello, and then you send it to the network. This is maybe one of the most important thing to get 3GPP to standardize, because here 3GPP standardization is very much needed for interoperability between the phones and the networks. Another 3GPP part, which is partly Ietf, is EAP, aka. So Ietf has standardized EAP, aka, with forward secrecy, dropped from RFC from Ericsson, and Nokia is now working on making that quantum secure. These you can use in 3GPP networks, but only in private networks, not in public networks, which is a bit weird situation. I would say maybe that's cryptographically, that's maybe the biggest weakness in 5G. I hope it really will be solved in 6G. So today, if some hostile nation is stealing the keys, like they did in Singapore, there was also an attack on Gemalto 10 years ago, then they can eavesdrop on all calls in a mobile network. So it makes a lot of sense to have ephemeral Diffie-Hellman. Here is the other parts of the 5G network. You have, of course, management, which also uses a lot of TLS. And then you have the application layer and the infrastructure layer. And of course, all of these needs to be migrated as well. The connectivity layer is very much built on standardization. the application layer and the infrastructure layer is not as standardized. There is quite a lot of standards for different application layer in 3GPP, GSMA, but the infrastructure layer is mostly up to the vendors. But of course, the vendors use Ietf and other standards here as well. In the application layer, also a lot of Ietf protocols. The only problematic is this Mikey-Sake, which use peering-based cryptography, but this is used for national safety, public safety. It's actually published in the RFC, but it was not produced by a Ietf working group. Then we have the infrastructure layer, which is not standardized, but this is definitely a high value target. If a hostile nation can replace the firmware in all the base stations in a country, that would be a very, very serious attack. So making firmware in base stations post-quantum secure is definitely a high priority. Not only because it's a high value target, but also because it takes time, and typically base stations live for 20 years. We notice when one operator don't use them anymore, they are moved to another operator in a developing country and continue to be used for 10 more years. That's not uncommon. This is something I cannot talk for other vendors. This is something we at Ericsson has been working on for several years, and we are likely to support strongest security levels of algorithms for firmware update. This is the current projection, and we choose the highest security level just because there is so much uncertainty with different government recommendations. So you cannot take the chance that we rather take a small performance loss than not being compliant with some countries' regulation. Right now it will be standalone, so not hybrid, but hybrid can be added later on the firmware software layer above. But unclear if that is needed. US is recommending this, and I think all European countries that require MLDSA in hybrid, they are recommending SLH DSA. One thing on this, a lot of these interfaces are non-constrained. So a lot of the use of public key cryptography in 3GPP networks are not very constrained. These are data centers, there are interfaces, and they are very long-lived. So you set up an interface connection and you keep it for a day or a week. A lot of there's use of TLS, there's use of DTLS, there's use of QUIC, and they all typically are used as replacement for IPsec. So you set up them once and then they run for a long time. So what are the 3GPP timelines? So 3GPP work in generations. You have probably all heard about 4G, 5G, 6G, and for everybody working in telecom standardization, 5G is already old, and it's already 6G is starting. So 3GPP has been working with 6G requirements for 1.5 years, and now started with 6G studies. And in 2027, they will start with 6G specifications, which will be done end of 2028-ish, and probably deployed 2030. There might be this is some internal Ericsson picture. There might be, the official timeline might be slightly different with a couple of months here and there, but I think this is quite accurate, high level. My expectation would be that 6G will be quantum resistant from the start, at least on a standard level. Then when the products and deployments is a different question. Question will of course come after the standard. Based on the urge of this, I would expect 3GPP to focus on MLChem, MLDSA, and SLH. DSA, they are basically only alternatives right now. But this has not been discussed super much in 3GPP, so I cannot say that 3GPP will do that, but that seems very likely. And it's definitely what Ericsson thinks 3GPP should do. These are global standards designed by cryptographers for all over the world. They're published by NIST, but I would say maybe the majority of cryptographers actually are from Europe. Europe has been very successful in doing post-quantum cryptography. In addition to your standards, of course, we need implementations, typically hardened implementations, sometimes certified. And sometimes not just by NIST, by Ietf. So some might have other timelines, but people saying that this is not a hurry for telecom, at least for me and Ericsson, this is quite urgent to meet the 2030 to 2035 timelines. We need Ietf standards and implementations, not only for encryption, but also for signatures in all protocols that we use. Right now, the status in 3GPP is that 3GPP has started a study here in release 20. Ericsson was driving quite hard to start normative work right now, but that will not happen. But I think there is agreement in 3GPP, not written down, but there seems to be consensus that there will be normative work in the end of release 20, which would mean 2 years from now. I think that's a little bit late. Then most vendors will already have implemented and PQC will already be deployed. So I think it's quite urgent to start normative work now. But let's see what happens. A difference between telecom SDOs and Ietf is that telecom SDOs really like RFCs, and a lot of people dislike code points from drafts. I would have a softer view on that, but that is very much people in telecom SDOs are expressing that they really want RFCs. I hope Ietf can produce RFCs for example, SLH DSA is a discussion topic now in TLS. If it's not working group adopted, I hope it can be AD sponsored or independent stream. One thing 3GPP people does not really matter what kind of RFC, standard track or informational, nobody really understands or cares, but RFC they want. And if this not happen, I would expect LSS. Nobody wants license statements. So what kind of requirements do we see from different bodies? Good. So we are now seeing, a few years ago, we had NIST standard publishing these standards. A few years ago, we saw some conflicting requirements with some European countries not recommending MLChem and MLDSA, but that was before the final standards was published. Now, to my knowledge, all European countries are also recommending MLChem and MLDSA. One important difference is that some European countries, like BSI and C, they are strongly recommending or requiring that MLChem and MLDSA is hybridized, while NSA for US national security systems strongly and also the UK now are very strongly requiring that it's not hybridized, which creates a problem for global industries like telecom. We cannot have very many different algorithms. That creates interoperability problems and increase the cost. Uh, Security levels, we're seeing that many governments are recommending level 3 or above. So my expectation would be that the telecom sector will also do that. We are critical infrastructure after all. Some governments recommend SLH DSA. I think that works for a lot of 3GPP use cases. That it's not in CNSA 2.0 means that the deployment status is implementation and deployments is a little bit behind, but I think we are seeing now quite a lot of implementations of that also. LMS and XMS, there's also different requirements whether you should use single tree or multi-tree. If you do hybrid, which elliptic curves should you hybridize with? Globally, our view is that NIST P curves and brain cold are increasingly seen as regional algorithms. We have full trust in P384 and we use it in our products, but we're hearing a lot of customers, they read safe curves, if you know that website, and which says that NIST curves are insecure and they come to us and complain. So we are increasingly thinking of curve 25519 and curve 448 as being the globally preferred curves. They are also, I would say, more secure and better performance, but security-wise, I think the old curves are good. But our thinking, Ericsson's, not the telecom in general, is to move as much as possible to these curves if we still are using elliptic curve cryptography. Then we're seeing some governments recommending SHA-3. It's a quite natural choice in the migration as it's used internally in MLChem and MLDSA. It also has quite nice security properties, much less complexity and much better side channel resistance. But SHA-2 is of course fine and can be used for legacy reasons. Sometimes just much easier to use what you already have. Then we have a bit more question marks with South Korea, China, and Japan, which is to some degrees developing their own PQC algorithms. I have a bit big uncertainty whether these will be required and how much they will be used. But that's the status. And this is, of course, complicating for any global business. So security levels, these are the NIST security levels, and instead of traditionally talking about 128-bit security and 256-bit security, NIST have moved to 5 security levels, 1, 2, 3, 4, 5, which are all based on symmetric crypto. So AS128 is the basis of quantum resistant security level 1. And one of the reasons for that is that bits of security works when the attack algorithm can be perfectly parallelized, but a lot of these quantum attack algorithms like Gruber's algorithms cannot be efficiently parallelized at all. So symmetric crypto will not really be affected practically, and 4G and 5G will remain secure for the foreseeable future. I would expect 3GPP to mostly go for level 3, 4, 5 in the future, as that is recommended by a lot of governments. Now, is to use hash-based, I think security level 1 is perfectly usable for a lot of use cases, but telecom critical infrastructure will probably go for the lower part of this. But if you have IoT devices, I don't think you need to. Here are some statements of symmetric cryptography. This is an Ietf statement sent to Etsy, and this is a 3GPP statement sent to 3GPP. Basically saying that symmetric crypto will remain secure. Attacks are not practical. and they can continue to be used. For a lot of these have been about AES. 3GPP states that these also apply to basically all 128-bit symmetric algorithms, like SNO 3D, SUC, TUAC, KMAC, ASCON. Basically, the key length is the main determinant factor in the attack complexity. That said, 6G will very likely use high-performance 256-bit algorithms. Another good calculation by Samjak is that to break a single AES 128-bit key, you would need qubits that would cover the surface area of the moon. And he concludes that that is unlikely to happen in my lifetime. And now we are seeing, this is a NIST statement. There's a similar statement from the UK government that basically all 128-bit symmetrical algorithms can continue to be used. So if they are secure against classical computers, they're also secure in the future against quantum. But if you do something new, you can move to 256-bit anyway. Here is the symmetrical algorithms in the current 3GPP. 3GPP started the study early based on symmetrical algorithms, based on several reasons. One was compliance with government requirements if you sell to governments. Another was performance issues. And the third were worries about quantum attacks. And that led to 3GPP standardizing, specifying new 256-bit algorithms. So now there are 256-bit algorithms for authentication key generation, and there will be for radio and encryption. But they're likely not deployed yet. As you can see in this, 3GPP has a history of standardizing several algorithms. So there's, for authentication key generation, there's both one based on AES and one based on Keccak. When updating the AES1 to 256, 3GPP and SSH decided it was actually much simpler to use Reyndal 256. That's the AES relative with the 256-bit block size, which is now also likely to be standardized by NIST in the future. One weakness or one cryptographer typically don't use is that 5G uses 32-bit tags. But to my knowledge, this has never led to any practical attacks at all. This is not the weakest link. And typically you need to forge several messages to actually do anything important. Typically you have encryption. Typically what is transported is typically HTTP with strong protection over the top. So this is more protection for media calls and for metadata, so nobody can fake the IP address. And the worst thing that happened then is they sent to the wrong address. Based on this study, ETSI-SAGE, which is the crypto group in ETSI, which 3GPP is related to, specified new 256-bit algorithms. ETSI-SAGE is a little bit like CFRG here in Ietf, if you should compare to something. And now 3GPP is not worried about quantum attacks on the symmetrical algorithms anymore, but these new algorithms have a lot of benefits anyway, so they will very likely be used in 6G, even if no decision has been made. These new one thing that is new is that they are A80 algorithms. A80 algorithms is not really exciting if you work with TLS and IPsec. It has been the default for a decade or so. But 5G still use separate algorithms, but in a secure construction, and has done so since 3G. The compositions in telecom are secure, not like the ones in TLS and SSH. The benefits with this new are that they're much faster in software. They have longer than 32-bit tags that behave like idiomax. By being 256-bit keys, they comply with some government requirements that not always make sense, but governments have requirements and you just need to follow them. If they say you need to have 256-bit keys, you cannot. It's hard to argue that it doesn't really apply to this use case because it's inflexible. And with these longer keys, you get improved security against multi-key attacks. We try to break one key out of many. So with the publication, if you follow the standardization, these FIPS 203, 204, 205, which is MLChem, MLDSA, and SLH DSA, they were published last year, like a year ago, and they have already seen massive, quite large deployment, at least on the web for hybrid chems, X2511 MLChem 768 is already Cloud4 reported like 35 or 40% of client hello, which is a lot in such a small time. OpenSSL, which is used in a lot of telecom interfaces, already supports MLChem, MLDSA, and SLH DSA. And this is the long-term support version. And OpenSSL, which is also used in basically all telecom products, even if it's not part of any standards, are now using MLChem 768 as the default key exchange. And a few months ago, I saw that quite many, like 3-4 different IPsec implementation started supporting MLChem. So for the key exchange part, you just need to update the software and you are quantum resistant. For signatures, will probably be a couple more years. You need to upgrade your PKI and spread roots of trust and so on. It takes time. And I think the PKI for these are not really ready yet. It will, there's very little, if any, certified HSMs, and there are some standards if you want to use Web PKI, which is quite driving. Then browser forum, CA browser forum is quite dominant. They don't have standards for this yet. As I said, 3GPP and the telecom has been in the past, always tried to use backup algorithms. So 2 different algorithms supported in all nodes that are based on very different constructions. Now, in the first deployments of PQC, that might not be possible to have 2 different algorithms, so that might have to be added later. But MLChem and SLH DSR, this is lattice-based and this is hash-based, so it's very unlikely that both will be broken, and hash-based is very conservative to start with. For MLDSA, I mean, for MLChem, I think HQC and classic McEllis are quite good backup algorithms. HQC for ephemeral key exchange and classic McEllis for static keys. I think the reason for this is if one of them is broken, you can very quickly change to the other without any major problems. And in the past, maybe theoretical attack was common. That's very uncommon now that you have a theoretical attack that decreases the security to 0 of something that is deployed. Implementation bugs are maybe much more likely. You have some implementation bug that you cannot fix, or it takes time to fix, and then can just switch to another algorithm. And that's the end. Seems to be alignment in governments in a lot of the words around MLChem, MLDSA, and SLH DSA. For telecom, this migration is driven very much by government requirements. This is something we need to do, and we need to do it urgently. Telecom will probably use very conservative options. Symmetric crypto will continue to be secure and used. 4G and 5G will remain secure. QKD and QRNG and also doubling symmetric key are mainly distractions. Distractions are dangerous if you think migration is important. And mobile network standards and products will have to and will soon support PQC for both 5G and 6G. The 3GPP standards, typically TLS and IPsec, are done in profiles that apply to all generations. So you just need to add PQC in a single place, and it automatically applies to all TLS or IPsec used everywhere in 3GPP systems for all generations. But then it's of course up to the vendors whether they want to update all the generations to the new release or so on. But the standard will be there. So I think we have 10 more minutes for questions and discussion. Happy to answer any questions about cryptography in mobile network. John. Yeah.
Thank you. That was both interesting and quite clear. I'm just one. I don't know all that much about the architecture of mobile networks. I'm wondering to what extent do you think that providers will in fact upgrade their 5G systems to use PQC? You know, how likely is it, for example, that Google will push PQC out into my Pixel phone? It's a 5G phone, but it's not the most recent one.
Yeah, for the phone, I don't know. I guess they will update. If you get updates to Android and so on, you will get updates. But I think you have to ask Google about that. I guess they will be limited, not more than usual updates after a few years. I think for them in the infrastructure part of the mobile networks, my feeling is that operators are very on top on this, and they are pushing us. There are operators coming to us asking Ericsson, when can you be quantum resistant? Can you be 100% PQC by 2030? Yes, no. Yeah, that's the dialogue we are having. So I think in the infrastructure, it will definitely happen in deployments. Your mobile phone, ask Google or
okay.
Yeah.
Hi, Jean-Michel Combe from Orange. I have 2 questions. Maybe you come back to the slide 4, please, about history.
Yes.
Yeah, correct. 2 questions about the sentence QKD forbidden to use in Ericsson products. First question, is it a definitive decision?
No, it can change any time, but it's a very new decision because before it was maybe not seen serious, and now people are talking about it as a viable product. And but it's very obvious that this is not the approved security thing from if you talk to governments, and typically that is what. Okay. To be used in telecom, typically we need global governments to say this is approved security solution.
Okay, so yeah. that was my second question.
Yeah,
it's not why approved, was the reason?
Yeah, it's not approved for security. If you want to deploy it as a non-security communication, I don't know, it doesn't hurt, but it doesn't help either. The availability and is so bad you cannot rely on it, and there have been a lot of practical side channel attacks. So I would say QKD is a distraction and a dangerous one.
Okay. So the second question was why. So to summarize, this is because national bodies don't recommend to use it.
Yes, but also because they are right in their assessment.
Okay.
Yeah.
Sama to you, Tresson. Thank you very much. It was a very comprehensive view. And I have a question regarding slide 11 when you were mentioning about remote attestation. And I was wondering how much of it can IETF take, for instance, in RATS working group? And if I understood correctly, you are saying that it's not standardized by 3GPP, including remote attestation, right?
That's my understanding, maybe, but it's not really my topic, so I could have missed something. But most things in the infrastructure layer are up to the vendors, and then the vendors like Ericsson, Huawei, Nokia have to choose. But typically they would use some standards, but they would be free to use whatever standard they want, like RATS or something else.
So they are, acceptable. So RATs standardized, they would be acceptable for them, right? If something like that is standardized, they would be using that. Is that correct?
That seems likely.
Okay.
I don't know what competing standards there are for remote attestation, but I think all vendors, including Ericsson, we would like to take existing standards like an Ietf standards and then use that. And sometimes sometimes Ericsson would buy the hardware from a other company, and then might be up to that company with which remote attestation to implement. And Ericsson just say that we accept that. Yeah.
Okay, sure. Thank you very much. So one very quick question as well. So what do you think is the typical lifetime of such a connection? Just thinking in terms of remote attestation. So what is like typically when you say long term? So what typically would it be the lifetime of the connection?
For remote attestation, I don't know, but for IPsec and DTLS and TLS in mobile network, I've seen that they're often running for days. They might run for weeks and maybe up to a month. The lifetime of the connection.
Thanks.
Yeah, thank you.
Thank you, John. Thanks for a nice talk. So would you also please to share a little bit PQC standardization progress in ISO? Yeah.
The standardization progress.
Yes, that's right.
In NIST or IETF or 3GPP. ISO, yeah, I'm not following ISO at Ericsson. We have decided that paywall standard is a cybersecurity problem. It increases the risk of implementation errors, and it very much, because it's so much harder to check that the implementation is correct. The cost is not prohibitive, but all the processes to get the right to buy a lot of standards and check this is hard. Also seen examples of vendors implementing from Wikipedia instead of buying the standard. They think, and typically it's compatible, but they miss a lot of the security requirements that, yeah. Thank you. Seems to be the last question. If anybody have any more questions, feel free to grab me in the corridors. And if you want the slides for some reason, the recording will be published on YouTube as normal in a week. And if you want the slides, that can be arranged.